Okay, so it's my pleasure to introduce Jan Vonk from Leiden University, who will talk about singular moduli for quadratic fields.
All right, thank you very much. Can everyone hear me all right? Okay, that looks like some shy nods in the back, so I'll take that as a yes. So today I would like to talk a little bit about singular moduli, primarily in the setup of real quadratic fields. And everything I'm going to say is joint work with Henri Darmon. And I'd like to kind of, I'd like to tie it up with everything we said also last week. So I talked last week during the summer school also about the work of Gross and Zagier. And one fatal error that well, not error, but one unforgivable choice I made is to not really talk about the proof. And so I would like to atone for this sin today by focusing in a little bit more on the mechanics of the proof, the statements of which we've already seen, as well as some of their arithmetic applications. So I'd like to begin with imaginary quadratic fields, which is a much more classical theory. And I'd like to highlight some of the aspects that I will hone in on. Imaginary quadratic fields. Where the study of complex multiplication really has a very long and rich tradition, starting sort of in the late 19th century. And in the early days, the theory of complex multiplication which I will abbreviate by CM henceforth, was really all about the study of special values of modular functions at CM points. The CM points, I'll denote by tau, they will be contained in the Poincare upper half plane. And a CM point is a point in the Poincare upper half plane that satisfies a quadratic equation with, let's say, integral coefficients, or integer coefficients. And there's two very important types of these invariants that you see show up in the classical theory that I'd like to focus on. And they behave very differently, arithmetically speaking, one of which are the singular moduli. And singular moduli are special values of the Klein J invariant at such CM points. And they're known to be algebraic integers. Okay. And so in the notes from the course last week, we saw proofs of this. And we saw actually a proof in the notes that takes advantage of the elliptic units as well. So elliptic units will be special values of Siegel units at CM arguments. And I won't define these precisely. I just want to give you a flavor of what they look like. They're also known to be integers, at least away from a finite set of primes that is going to be determined by the specific Siegel unit that you chose. So they're n units. And so to just illustrate that with a little example, I would like to tell you about the J invariant of the square root of -14. And if I was doing a slides talk, I would tell you what that number is, because it has an explicit expression in radicals due to Weber. But to minimize the amount of things I have to write on the board, I'll only tell you what the norm of this algebraic integer is to Q. Yes, it does. I'm not really going to talk about them, so I don't want to specify what this V is, but V is going to be, oh, sorry. Yeah, it's a V. Yeah, so V is going to be a vector of length 2 with coefficients in Q modulo Z, where the denominators can only be divisors of n. So that's what this n is. So that's how V determines n. So the norm of this algebraic integer down to Q is an actual integer, and I'll tell you how it factorizes. So 2 to the 24 times 11 to the 6 times 17 cubed times 41 cubed is the norm that comes out. So this is a very nice algebraic integer in a cyclic degree 4 extension of Q joint square root of -14, and this is its norm. So in contrast, I'll take also a combination of such elliptic units, namely the following. I'll take the Ramanujan delta function, I evaluate also at this argument minus 14. Now, of course, this is a modular form of weight 12. We'd rather have a function, and so we can take an eta quotient, for instance, like the following one, minus 14. Again, this is a very nice algebraic number in this C4 extension of Q joint square root of minus 14, which I could tell you, but I'm just going to tell you its norm, again, to minimize the amount of numbers I have to write down on the board. And here we get 2 to the 24. And the 2 is here, the n in the general picture. And so we see that they have very different behaviors. These invariants, these elliptic units, they're very clean somehow. Their factorizations are entirely focused at primes above 2 in this case. Whereas the singular moduli, they're a little bit all over the place. They have lots of very rich factorizations at various primes. So they behave very differently. Nonetheless, they satisfy important relations between them. So in fact, these relations lie at the core of the proof of the main theorem of CM theory that I gave in the notes, which is really the most classical proof. So they were used. Well, let me just say they were used in the proofs of the main statements of complex multiplication as well as computations. So maybe some names to mention here are Weber, who has a book that contains all of the computational methods to obtain numbers like this, and he used exactly this kind of technique. He first determined these elliptic units, in fact, specifically this one, and its two siblings, and from these relations, he determined the J invariant itself. These specific examples you can also find in the notebooks of Ramanujan, who used a very similar technique, even though the language was quite different, to determine precisely those numbers, or precisely those singular moduli. It's using these relations between singular moduli and elliptic units. Now, famously, this also came up in the proof of the class number 1 problem, which was also mentioned this morning, due to Hegner and Stark. They proved the class number 1 theorem by considering in what nowadays we might like to view as a consideration of the following diagram. So they were looking really at the normalizer of a non-split Cartan curve with 3-level structure, as well as a non-split normalizer with 8-level structure. Now, both of these curves are isomorphic to P1. And if you look at their works, you'll see that they write down explicit isomorphism. So you see in their works show up a canonical cube root of the J invariant, which happens to be a uniformizer on the non-split 3 curve. This is isomorphic to P1, and this isomorphism is described by this cube root of J, which they call gamma 2. There are also the Weber functions, which are examples, they're combinations of these Siegel units that I mentioned before, which they use to write down an explicit isomorphism of this curve with P1. And of course, both of these lie above X1. So, and well, it doesn't really matter. What does matter is their fiber product, or so the curve, rather, non-split 24 that lies above both of these. Now, what they did is they used the main theorems of complex multiplication, and namely, they used also the integrality statements that I've implicitly used here. So the fact that J invariants of CM points tend to be integers can actually be sharpened to this cube root of J function. And so nowadays, of course, by thinking about it geometrically, we understand this much better. And the mechanism of their proof is that suppose you have some, I say large, maybe I should say small. I mean, it's a negative discriminant which in absolute value is very large. And suppose it has class number 1. And suppose it's one of the ones that we don't have yet on the list. Now, if this is true, automatically, it is forced upon this discriminant for the primes 3 and 2. If they don't divide it, they must automatically be inert in the quadratic order of that discriminant. That's kind of the key principle in the strategy of Heegner. The observation that by this inertness, any such discriminant gives rise to an integral point. On this non-split 24 curve. Now, how's that helpful? Well, you see, this is where we wouldn't have come by with these two curves individually, because having an integral point on P1, there's of course plenty of integral points on P1, because there's infinitely many integers. Nonetheless, by considering the fiber product instead, we pass to this larger curve, which just hits the sweet spot of being of higher genus. It's actually a genus 1 curve. And therefore, having only finitely many integral points, and in fact, I can tell you the equation that you see show up in their works is precisely this in short Weierstrass form. They have a quartic model for it, but nonetheless, this is the curve that is relevant to their work. And so they reduce the problem by the statements of complex multiplication to the determination of the integral points on this very explicit elliptic curve, for which you can use any number of methods you like, but that's really at the core of their proof. And so here is that principle that makes everything tick. All right. So of course, we've studied this a lot, and we saw already this principle in action in several of the talks. And this gives you this very nice perspective about CM theory, giving you a systematic construction of rational points or integral points on modular curves. No, so this one will just be, it'll just be a cover of these two. Yeah. You're asking, they all have Hecke operators, but the existence of this is just a forgetfulness. Yeah, exactly. You forget half of the structure if you go through this, and you forget half of the structure when you go through this. Yeah. Okay. So this is all about the study of individual rational points provided by the theory of complex multiplication. Now, what happened a little bit later, well, much later actually, in the 80s, is Gross and Zagier started studying the interaction of various Heegner points with each other. And that's really what I would like to focus on today. So what Gross and Zagier did, we already saw a lot about their work last week, but it all started with the following consideration. So what they did is they studied the factorizations of the difference of two singular moduli. So they will look at J tau 1, where tau 1 is a CM point in the upper half plane, subtract the singular modulus corresponding to tau 2. This gives you, of course, still an algebraic integer. And what they do in their first paper, which is really contains all of the core ideas of the follow-up paper that we talked about last time, is they study the norm to Q of this specific algebraic integer, which of course yields an actual integer. And they look at the prime factorizations of these. And we already saw that the individual singular moduli have very rich prime factorizations at lots of primes. And what they do is they kind of generalize that, because of course, J of cube root of unity is equal to 0. So as a special case, you get a single singular modulus back. But here they study really the fully general case. And what's amusing is that all the prime factors that appear in these factorizations only occur at primes that must be non-split for both of the discriminants that go into tau 1 and tau 2. And in fact, here already we kind of saw this. So we only have a single one here, but all of these prime factors are all non-split in Q adjoined the square root of minus 14, which you can check. And the other one is Q adjoined the square root of minus 3. It's kind of hidden because the J invariant is 0, but the same statement is true for that. Okay. Now, what they do is they consider the following diagram, and this is kind of the part of the strategy that I'd like to focus on for the remainder of the talk, because we'll see it come back in a very different context. If we take the two imaginary quadratic fields, in the case of Gross and Zagier, obtained by adjoining tau 1 and tau 2 to the base field Q, so this is Q tau 1, this is Q sorry, yeah, this is q tau 1, that's q tau 2. And then we have an intermediate quadratic field, which is obtained by adjoining the square root of the two discriminants. And both of these discriminants are negative, and so their product is positive, and this is a real quadratic field arising in a diagram like this. We have a biquadratic CM field, which contains this real quadratic subfield F that will play a very large role in their proof. Okay, now what Gross and Sagier do is they give actually two proofs of their factorization formula. And the proofs are so much more interesting than the formula itself, so I actually won't state the formula for this integer that they prove, but I will talk about one of the two proofs that they give. Now, Gross and Sagier do the following. So they compute the Fourier coefficients of a certain real analytic family of Hilbert-Eisenstein series. And it's actually a very famous family, E sub S. I could define it for you, but I'm not sure how useful that is. I'll just tell you that it's a weight 1-1 real analytic modular form on the group SL2OF. So it has full level 1 structure, and it's defined over this base field F. F is a real quadratic field, so such a modular form has two weights, and those two weights are both equal to 1. And S here is a complex parameter that can vary. Okay, so they study a certain family, which was written down by Hecke, and their strategy looks roughly as follows. When this parameter S is equal to 0, so the specialization of this family, this Eisenstein series is associated to the induction of the trivial character of this biquadratic field down to F. And if you look at its Fourier expansion, you'll notice that, in fact, this series is just trivial. So it's not a very interesting series in the specialization. The Hilbert modular form, it's weight 1-1, it's holomorphic, but actually it's 0. The family that passes through it is highly non-zero. So it's an interesting deformation, really, of the 0 form that they consider. In fact, there's a bit of history behind this. So Hecke, when he first wrote down this family, his goal was to construct a non-trivial element that's holomorphic and weight 1,1 of full level 1. And so he did his usual regularization trick, which is what this parameter S is, specialized to S is equal to 0. And then all he needed to show was that the specialization was non-zero. And he did this by checking the sign in the functional equation of the constant term. But unfortunately, he made a sign error. And so he thought he'd shown that it was non-zero, but in fact, the sign was the opposite of what he thought. And it proves, in fact, that this series is identically equal to 0. So for Hecke, this was bad news. But for Gross and Sagier, this was good news. Because what they do with this series is they say, we have a real analytic family of Eisenstein series, and it vanishes at the specialization. So I can now take the first order derivative of this family with respect to the parameter. Gross and Sagier, they compute the Fourier coefficients of the series obtained as follows. So they take this family, ES. It's an analytic family varying with a parameter S. They take the first order derivative of this series, which is now the leading term in the Taylor series of this family, because the specialization vanishes by Hecke. Once they have this series, it's a real analytic modular form of weight 1-1. They're going to restrict it to the diagonal, so setting both of the variables equal to each other. And the end result is an analytic form of level SL2Z and weight 2, 2 being 1 plus 1. It's an analytic modular form, and so to get a holomorphic modular form, they apply Sturm's holomorphic projection operator. So this is the form that they consider in the end. So they apply all of these various operations to it: first order derivative, diagonal restriction, and holomorphic projection. So that's 3 important operators in their work, and out comes a modular form of weight 2 and level SL2Z. Now, I told you they compute the Fourier coefficients of this family. And you can imagine doing this because it's a family of Eisenstein series. So it is a very explicit Fourier expansion. And now you can do all of these operations to it. First, you compute the first order derivative, the diagonal restriction. You can calculate your way through it. Even the holomorphic projection you can calculate. This is exactly what Gross and Zagier do. And what do they find? They find an expression for all the Fourier coefficients, but the first one is very pleasant. It's actually equal to the logarithm of the norm down to Q of the difference of the two singular moduli. So exactly the quantity we wanted to prove something about, plus some error term. And this error term, I will not tell you, there's an explicit intersection number times log Q for every finite prime Q. This comes out of their calculation. Now this is a finite sum, I should also say. So there's only finitely many contributions in this sum, and it's the error term to the first Fourier coefficient being precisely this. Okay. On the other hand, and some of you may have spotted this already, we have another expression for A1. It's 0. Because this space of way 2 modular forms have full level SL2Z is trivial. So this modular form is entirely 0, and in particular, its first Fourier coefficient is 0. If the first Fourier coefficient is 0, you get exactly a relation that this norm, whatever it was after you exponentiate here, is precisely given by a very explicit factorization formula. And that's the main result that they state. I won't care so much about the explicit formula, which is why I didn't tell you what this factor is, but that is the shape of their proof. Okay. Now, of course, we've seen already last week that there's more to this picture. And if you stare at this expression, the calculation that they did is really a calculation of a height pairing between the two Heegner points defined by tau 1 and tau 2 on x of 1. Oh, so sorry, I didn't do this right, but something like this. So these are the contributions local contributions, I should say, to the global p-adic height pairing of the CM points associated to tau 1 and tau 2, which is the neuron height, on the modular curve x1. That's another way to see it's 0, because of course the modular curve x1 is isomorphic to p1, so its Jacobian is trivial. This height pairing is also 0 for that reason. And that's really what in their later work, all the calculations that they did here, amount to really the calculation of the height pairing between any two Heegner points with some mild conditions on the discriminant. The first paper being where the two Heegner points are really the same. That's the Gross-Zagier formula. And then there's Gross-Conen-Zagier, which is for co-prime fundamental discriminants. Similar technique. Okay. All right, so that's kind of the shape of the proof. That's the main idea of their analytic proof of this factorization formula. And a few things are notable about it because they give also a second proof, and the second proof you can already imagine how it is. It's the one that comes more naturally to an algebraic number theorist. It's to say that, well, j tau 1 minus j tau 2, if a prime divides that, these correspond to two CM elliptic curves that reduce to the same curve modulo that prime. Yeah? And if the CM discriminants are distinct, then the only way that that's going to happen, because you get an injection on the endomorphism rings, is if that curve is supersingular, then its endomorphism ring is a maximal order in a quaternion algebra, and then you start counting embeddings. That's kind of the first proof that they do, but it relies on the theory of complex multiplication, specifically the notion of a CM elliptic curve. So that's an important point to make. The second proof, which is this proof that I sketched here, doesn't use CM theory at all. And that's kind of a remarkable thing about it. It doesn't ever make any reference to the fact that the individual J invariants are algebraic numbers. You don't really need that in this proof. And that's a very important idea in what is to come. Okay. All right. So, okay. Let's now go to a setting that is a little bit more mysterious. And that's the setting of real quadratic fields. So of course, all these developments in complex multiplication have led to lots of very interesting applications. So we'd very much like to generalize it to other number fields, real quadratic number fields being the simplest case where it's not so clear what to do at all. And so we would like a theory of what we might call real multiplication. Rm. And what should such a theory do? Well, it should incorporate all of the aspects that we've already discussed so far. Yeah? Now, it's quite difficult to do this in the most naive way, because, for instance, if you're thinking of singular moduli, the J function is not defined at a real quadratic singularity. The real quadratic singularity is just outside the Poincare upper half plane. The problem being that infinity splits in a real quadratic field by definition. So the prime infinity is kind of the wrong prime to consider there. So for that reason, it's convenient to work p-adically, where we switch from doing complex analytic constructions and the prime infinity to p-adic analytic constructions and the prime p, where p is chosen to be inert in the real quadratic field that we care about. That's the analog of an imaginary quadratic field having the property that infinity is inert by definition. So ramified would also be fine, but for simplicity, I'll assume inert because it's a little simpler. In fact, for anything I'm going to say today, it doesn't actually matter. So let me just say non-split. Yes, so to work p-adically, where we would like to evaluate, again, some analytic objects at Rm points. The analytic objects will no longer be modular functions, but one way to approach this problem is to evaluate certain co-cycles at Rm points tau in the p-adic upper half plane. And the p-adic upper half plane is a very nice rigid analytic space whose CP points are P1 of CP minus P1 of QP. So it would be analogous to P1 of C minus P1 of R, which is the union of the upper and lower half plane. P-adically, this space is nice and connected already. Okay. So the very first thing that one would like, in lieu of all these nice geometric structures that exist already in the complex multiplication case, is at least an analytic construction of invariants of both of the types that we've seen before. So we would like to have a good notion of singular moduli as well as elliptic units. Now, of course, we're not the first ones to think about this. Lots of people have considered this before, and in fact, tremendous successes have been booked in the case of elliptic units. In fact, so good that they well surpass all of the aspects that I've mentioned today. So Dasgupta and Kagde have completely proved Brummer's star conjecture, as well as have provided analytic formulae for them, essentially giving a really satisfactory answer to what elliptic units are for real quadratic fields. And in fact, they do it for generally totally real fields. A week ago, I would have said maybe that P had to be different from 2, but after Mahesh's talk earlier this week, I'm not sure I still have to say that. So essentially, we know everything we need to know about elliptic units, and in much more generality, really, than the humble situation I'm sketching today. What is much more mysterious still is the singular moduli. So these elliptic units will always be P units in abelian extensions of real quadratic fields. Singular moduli, we really only have conjecture. So this is a conjecture that I stated in previous work with Darmon, where we come up really with an analytic construction of some invariant that seems to behave in all key aspects as the differences of singular moduli do in the complex analytic case. So the construction associates to a pair tau1 and tau2 of Rm points in HP. And of course, if you have an Rm point in HP, this condition that P is non-split is forced upon you, not inside of QP. We attach an invariant which I'll call for the purposes of this talk, theta p times tau 1, tau 2. This invariant, I could define it for you, but that would eat up the rest of the talk, and I'd rather tell you a little bit about the strategy for proving some of the conjectures. It's an invariant that's constructed analytically based on the notion of rigid meromorphic cocycles. And the important thing to know about it is that it's completely explicit. It's an infinite product of very elementary quantities, and it returns a number in CP. In fact, CP star if tau 1 and tau 2 have coprime discriminants. What we conjecture is that under certain good circumstances, this should be an algebraic number. And this is the conjecture as you find it in DV1. In fact, we conjecture much more than that. We say exactly what the field of definition of these invariants is. It's the compositum of the two ring class fields associated to tau 1 and tau 2. And we also give a conjectural description of its prime factorization. Of course, the conjectural description is exactly the description that also appears in Gross and Zagier, where we formally switch infinity to P. And so instead of defining these invariants for you, I hope I can make up for it by showing you a couple of examples that we computed numerically to at least give you a taste of what kind of invariants these are. So I have a lot of input because with this construction, I can choose my two Rm points like before, but I can also choose my prime P. My Gross and Zagier were fixed at P is equal to infinity, but I can let that vary also. Let me choose two, the smallest prime, and let me choose for the Rm discriminants the square root of 5, as well as the square root of 21. So now we run this machine, and out comes a two-adic number that looks very convincingly like the following algebraic number. 48 square root of minus 3 divided by 7 times 13. And I'll say a little bit about these factorizations later on. Another example, and this is the part where I regret not doing a slides talk. It's a slightly bigger one, because this one doesn't really reveal a lot of structure yet. It's the same invariant, three-adically this time, so I took a different prime just for fun. The first one, I still take the smallest, still take a square root of 5, but for the second one, I take the square root of 221. Square root of 221 has class number 4. Yeah, so it's an interesting one. It's a cyclic group of order 4, I believe, and it's an interesting one to try and generate. So it satisfies up to very high precision the following polynomial. 6256 x to the 4th plus 1828 x cubed. Apologies for the numbers, but I just want to point out a few qualitative things about them in lieu of stating the conjectures very precisely. So it's a root of this polynomial. And if you look at this polynomial, the splitting field that it generates, we have Q adjoined the square root of 5. We have Q adjoined the square root of 221. The Hilbert class field of this one, the narrow Hilbert class field in a narrow sense, H2, and this one here, it's equal to H1. So this is I think it's a degree 4 extension, whereas this one is equal to its own narrow Hilbert class field, and the compositum of the two, so that'll just be a field up here, I guess, H1, H2, can in fact be obtained as the splitting field of this polynomial. We found this by analytic means. It seems to lie in the right field, but more excitingly, the prime factorizations also are very structured. So this is a 13. So if we look at this 7 and this 13, they have the same superficial property that Gross and Zagier already saw, but proved in a much more precise form. For instance, just what's easy to appreciate is that the 7 and the 13 are both non-split in both of these real quadratic fields. They're non-split in both of them, just like in Gross and Zagier. And the same thing is true for this 6256. So 6256 is 2 to the 4 times 17 times 23. And all the prime factors there have exactly the same property. Okay, so that's an easy kind of consequence of the main conjectures, but the main conjecture is very precise. And in fact, it gives an explicit description of what this factorization is. Are described as follows. They're actually equal to intersection numbers of geodesics associated to tau 1 and tau 2 on the Shimura curve associated to a maximal order in a quaternion algebra ramified at P and Q. So this might be some Shimura curve like so, where P is the prime with respect to which we did our construction, so the analytic prime that we chose, and Q is the prime whose prime factorization we're trying to determine in these invariants. Yeah. So tau 1 and tau 2 each give rise to a geodesic, closed geodesic, on the quotient. One might lie here, and then the other might, I don't know, loop around or something. By taking the geodesic, connecting tau 1 and tau 1 prime in the upper half plane, and just taking the image in the quotient that describes the uniformization of xpq. Okay? So a different Shimura curve for every prime q that we pick. If you look back at Gross and Zagier, a similar thing was going on. They were counting embeddings in the maximal order in the definite quaternion algebra, arising on the endomorphism ring of the reduction, which was super singular. And so therefore, that was a definite quaternion algebra ramified at infinity in Q. And so there isn't a Shimura curve, there's more like a Shimura set. It's a zero-dimensional variety. Here we get a one-dimensional variety, and the factorizations in tons of experiments seem to be exactly described by exactly these intersection numbers. So that's what the factorization conjecture looks like when you state it precisely, and you can find this in the notes. So in this particular example, this will be x3q. Yeah? So there will be three relevant Shimura curves, x2q, x17, sorry, x2 times 3, x17 times 3, and x23 times 3. So three Shimura curves show up there. Okay, anyway, so I'm not giving you the full construction of this invariant, but I'd rather talk about a kind of a strategy to try and approach these conjectures. And of course, the elephant in the room is that if we look at Gross and Zagier's work on the proof of these factorization formulae that we've conjectured in our first paper together, the first proof is already forbidden territory because it relies on the theory of semi-elliptic curves, which does no counterpart in this RM setting. So we have to completely avoid this. If we look at the second proof, however, which is there on the left board, that second proof is much more promising. And so we might try and generalize this because it doesn't rely on any notions of CM elliptic curves. It's just analysis, and real analytic families can be replaced by p-adic analytic families of modular forms. So we can try and see how we go there. Unfortunately, it's not so clear how to carry this out. And there's one big problem, which you can see actually in this example. If you look at this polynomial, there's something quite striking about it, which I'm sure most of you have noticed. It's palindromic. Yeah? And that's because complex conjugation is a very different beast in the complex theory and the real analytic theory. Complex conjugation actually forces the invariants to lie in the minus part. So whenever you complex conjugate it, you get the multiplicative inverse of the previous invariant. That's what you see here. Yeah? So whenever you get a root, you also get 1 over that root because it's the complex conjugate of it. Here also you can check explicitly that this is true in this example. And that's not so great because it shows that if you do something like Gross and Zagier, where you take the norm all the way down to Q, that's not going to be very helpful because the norm all the way down to Q is 1. So it's trivial. So this norm is much too brutal in our setup because it will immediately kill the algebraic numbers. They're not algebraic integers. They are, in fact, in the minus part for complex conjugation. So that already should be avoided. We have to look at Gross-Zagier and not take that average, not take that norm, which would be the average of all of the Heegner points of a fixed discriminant. We have to leave that behind us. So here, likewise, sorry. Maybe a further derivative, but that's not so clear to me. I think, in fact, it's much better to try and avoid the Eisenstein series altogether. And so to try and avoid the norm completely and just work with the first order derivative. I think what we're looking for in the case where we do take an average is proving that 0 is 0 or something, so that there isn't much to prove in the first place. It would be an interesting question to ask, what the second derivative is, but there I don't have a good answer for you. So this is going to be our approach, to try and avoid taking that norm and to look at this picture and replace everything that is a consequence of that norm by some object that is a bit more refined. So this ES in particular, the fact that we get an Eisenstein series is really caused by the fact that we take a norm here. So it's like, you see it very clearly here actually. An Eisenstein series, it's induced from the trivial character of this biquadratic field L over F. So that's also something we're going to have to get rid of. So in essence, the mystery now is, what do we do? I mean, we have all the steps of Gross and Zagier, but what family should we be applying it to? And in essence, that's one of the main difficulties really in this whole project, is determining precisely that. How do we carry out some analytic strategy of this form? Now, I can just tell you what the family is supposed to be, like some kind of deus ex machina, but I'd like to sketch at least, or give you some idea as to how you might go about systematically viewing this association of this Eisenstein series to the trivial character in a more kind of general framework. So I'd like to give you some kind of indication how you might want to think about generalizing what I'm about to tell you. So what we want is an analytic argument similar inspired by Gross and Zagier. That would be very nice. And analytic here means p-adic analytic. Okay, and the basic data that we have is the following. So we start with a pair of embeddings, K1 and K2, into the matrix algebra, but in fact, the proof applies equally well to any quaternion algebra B over Q. That is indefinite. And so for the original conjectures and the invariants whose examples I sketched here, this will always be the case where B is just M2Q, the matrix algebra. Okay, so that's the basic data. That's the data of the Rm points that we're given. They're given by such embeddings. And in fact, of course, we would like to have an integral structure to work with. So we'll want that this lands inside of a maximal order, the maximal orders of K1 and K2 respectively. So these are optimal embeddings, to put it in that way. Okay, now this kind of structure endows B with a very interesting linear algebraic structure. So the quaternion algebra B, it's a four-dimensional Q vector space, but actually it has an action of this biquadratic field L. And so I'll use the same notations that Gross and Zagier did, but of course it should be pointed out that K1 and K2 are real quadratic in our case, and they were imaginary quadratic in their case, but I'll use the same notation. So L is a real biquadratic field, and it acts on the quaternion algebra B. So we get an action of L on B by taking, so L is the tensor product of K1 and K2. And if I take small elements, pure tensor, K1 with K2, I make it act on B by the following rule. I just let K1 act by left multiplication on my element of B, which makes sense because I've embedded it inside of it, and K2 by right multiplication. Okay, and if you make this definition, it turns out that in fact, the reduced norm which exists on this quaternion algebra satisfies the following invariance property. So B1, A, B2, where A is an element of L, is actually the same as letting A sigma act on B1 and pairing that with B2, where sigma is the name for the automorphism of L over F. Yeah? So Galois group of L over F will be generated by this sigma. Okay, so you have this kind of skew symmetry of the reduced norm pairing on B induced by this specific action that we've put on the quaternion algebra. Okay, now B can now be identified also as an L vector space, yeah, of dimension 1. So it's identified with L, but not canonically so. And what we could do is the following. I'll draw a diagram for you to give you some kind of idea of where the series that I'm about to write down come from. So what we're going to consider is a space W, which will consist, it's going to be B, viewed as an orthogonal space with its usual reduced norm, tensored with a standard symplectic pairing, so Q squared, which is -1, 1, like so. This is isomorphic to B times B. This one has a symplectic pairing, this one has a orthogonal pairing, so I get the product pairing on W, which makes W into a symplectic space of dimension 8. So it's an 8-dimensional Q-vector space with this symplectic form defined on it. And in fact, I can tell you explicitly what this symplectic form is. If I take this notation from my symplectic form, it goes from W times W to Q. It's a tensor product of these two pairings here. And so the explicit description of that is that I take A1, B2. A and B are in W, so they can be viewed under this decomposition as an A1, A2. And I pair the A1 with the B2, and I subtract the pairing of the A2 with the B1. That's what I'm going to do. Now, what's nice is that if you identify B with L as a one-dimensional L vector space, this expression actually, up to some constant, depending on how you identified it, is equal to the trace from L down to Q, I should say, of the following expression. So A1, viewed now as an element of L through my identification, A2, and then B1 sigma, B2 sigma. This is the form that comes out. So I take this determinant of elements in L, and then I take its trace down to Q. Up to some constant, that is exactly what this form is. Yeah? Okay, now, why do I do this strange thing? Because it gives us some idea as to where this form should come from. So how we can view this construction of Gros and Zagier as a special case of a general construction that we might make. Okay, so inside of the symplectic group of dimension 8 that describes the symplectomorphisms of this space W, I have, well, by this decomposition here, I have the orthogonal group of B and the symplectic group of this space. Yeah? So that's O of B, and I have my SL2 over Q sitting inside it. So they both sit inside of there. The reason I'm drawing it in this strange way is because there's two more groups coming. There's a seesaw dual pair that describes the functoriality I'm about to use. Okay. Now inside of here, there is also a group T, which comes from my pair of embeddings that I've put inside of my quaternion algebra. And T is going to be the restriction of scalars norm 1, so norm 1 elements from L down to F. Yeah, so it's all the elements of L down to F. I can view this as an algebraic group. And it turns out to be accidentally isomorphic to the product of the torus coming from K1 and the torus coming from K2, fibered over the norm. So elements with the same norm divided out by Q star. So we have two descriptions of this algebraic group. This description here, the top description, shows you that this is, the T sits inside of SP8. It acts, you can see it, for instance, very easily on the definition there, because it's something of norm 1 here by this equivariance will act trivially on the symplectic form. Likewise, by this description, where is it, of the trace, oh, it's here, you see also that SL2F acts by symplectomorphisms on this, because F is fixed by sigma, so you can just change this base and it won't change the determinant. We have also a group SL2 over F sitting inside it. In fact, there's inclusions going this way. And then this is usually the notation that people use for dual reductive pairs. Up to a slight lie here, these are indeed dual reductive. This is a standard one, and this is a non-standard one that comes from the specific arithmetic situation that we're looking at. Now, what the theory of the Weil representation tells you is that you can lift an automorphic form from T up to SL2F. The other one in the dual reductive pair that sits inside of the SP8 that we've constructed. So if I start with an automorphic form on here, I can lift it to an automorphic form on here. And that's in essence what's happening in Gros and Zagier. What they're doing is they're taking a pair of trivial characters on this, or just a trivial character on the norm 1 torus, if you like, in any of these descriptions, and they lift it under this functoriality. So Gros and Zagier they take a pair of trivial characters, and out comes the Eisenstein series, at least in the specialization that they care about, which happens to be 0, so that's not a very interesting way to view this functoriality of associating 0 to something through this very highbrow picture. But the advantage is that now we can consider also non-trivial characters. And that's essentially getting rid of this norm. We're allowing combinations that are not just combinations with the trivial character, but also non-trivial characters can appear. So what happens if we lift a character chi1, chi2 under this lift? And that's essentially the form that I'll be working with in the analytic strategy. So out of this picture, let's see, I want to keep this on the board. Let me erase this example. Comes the following very concrete thing. I can write down what it is, so you can forget everything I said about this seesaw functoriality here, and just take it as your definition, but it's meant to motivate a little bit why you would consider such a thing. So what we do is we find an automorphic form which, unlike in the case of Grothendieck, does not need to be trivial. We call it the Steinitz form of alpha 1, alpha 2, where alpha 1 and alpha 2 seem like reasonable names to give to these two embeddings. They depend on these embeddings, and in fact, they depend on a lot less. They only depend on the isomorphism class of the maximal order as a projective OL module. So they kind of don't really know about the quaternion algebra. So it's an automorphic form on GL2F. It's going to be of weight 1, 1, and level 1. The level SL2OF. This will be the group, it'll be invariant after I put it up here through this seesaw duality. Now, okay, it's some automorphic form, but it's in fact a very explicit thing. So it's a linear combination. A very familiar series. It's the theta series associated to characters psi of this biquadratic field, L. And this is the bizarre thing. We started with a pair of characters on K1 and K2, and somehow we cook up this automorphic form, which is a theta series induced up from a character psi of L over F down to F. Yeah? So this will correspond to some standard theta series. This is the theta series, and the representation that corresponds to it is just the induction of that character down to F. Okay, so we now have this weight 1 modular form, just like Grothendieck, but it's a non-zero form, unlike what happened in their case. And the important question now is, how do we make a p-adic family that passes through it? How do we deform this p-adically? For Grothendieck, there was this formula of Hecke. The family was kind of the only interesting thing to consider. Here we might wonder in what sort of way can we deform this p-adic? Now, luckily here, we don't really have to do any work because someone already did all the work for us. So it's p-adic deformations, all the ways in which you can interpolate it into a family of Hecke eigenforms were all computed, they were all described, so parametrized. By Shaunak and Adele Bettina. And what they really do is they have a geometric picture that describes all of the ways in which you can deform this form in terms of the p-adic weight space, which contains the point 1, 1 that we're interested in. And then above it lies this kind of sheet, every point of which corresponds to a Hilbert overconvergent modular form, where in the specialization, we get precisely the theta series that we're interested in. This is this theta series, and then this sheet kind of describes all the ways in which you can deform it. And they already showed that the natural map to weight space, if you just keep track of the weight of the varying weight in this family of this Hilbert modular form, is in fact an Ital map. So they showed that. So it gives us a natural parameterization in terms of a very simple space of all the possible deformations that we can take. So all we need to do now is identify, well, I drew a two-dimensional picture, but it's really three-dimensional. It's a three-dimensional Latal sheet over a three-dimensional space. Is inside of this three-dimensional space of deformation, pick out the one that has the most relevant arithmetic information. So that's task number one. So we need to replace the Hecke-Eisenstein series, so the family by Hecke, with this p-adic one, which will be a suitable, and in fact, I'll tell you what suitable means in a second, deformation, which I'll call theta sub s, and then I'll put the p just to remember that it's a p-adic family. And it's going to be a family of cusp forms this time, not Eisenstein series, a full level SL2OF. At least in most cases, it's full level. There's a couple of cases where some small ramification caused by some two torsion. Okay, so that's step one. And in fact, I can tell you how to do that. In our parameter space, it turns out, for reasons we don't really understand, that the right direction to consider is keeping one of the two weights fixed to be equal to 1, and the other one varies. Can't tell you why. That's what rolls out of the algebra. That's the right direction to look at, the partial weight 1 direction. Okay, so once we have the partial weight 1 direction, there's a crucial second step. So this is all set up, right? So now we're in a situation, already most of the work has happened, and now what we need to do is the arguments of Gross and Zagier on this mysterious family. So that's what we do. So these are all quite heavy computations, but I'll just tell you what the result is that comes out. So compute the Fourier coefficients, just like Gross and Zagier, of, well, I take my theta series and I deform it in this way as a p-adic family. It's a family of Hilbert modular forms. It doesn't necessarily need to vanish, but nonetheless, I'm going to take its first order derivative. This first order derivative, I'm going to restrict to the diagonal. And I'm going to look at the point s is equal to 0, corresponding to the weight 1 theta series that we started off with. But we've taken the first order derivative now. This thing now looks like a weight 2 modular form, but it's still an overconvergent modular form. So we have to do an analog of the holomorphic projection, which is the ordinary projection on overconvergent modular forms of weight 2. And out comes a classical modular form of weight 2 and level gamma 0 of P. That's exactly the analog of what's there on the left board, all the way on the top, what they compute. Now what we need to do is we need to find the Fourier coefficients. And since I'm out of time, I'll just tell you the following. We find that A1 is equal to the following. It's the p-adic logarithm of the norm down to QP. Very important distinction with Q, right? This is not a global norm, it's just a local norm. So it's a bit like in the story of Gross and Zagier, instead of taking the norm to Q, just taking the norm to R, so absolute value squared of the invariant that Henri and I defined in our first work, tau 1, tau 2, plus an explicit error term, which is precisely the intersection numbers of the geodesics on the Shimura curve. I've drawn it in the example that I just erased. So intersections on xpq, where p is the prime we're working with respect to, and q is the prime that's varying here, times the p-adic logarithm of uq, the gross Stark unit associated to a choice of prime above q. We get an expression that looks on the nose exactly formally the same as the expressions that we found in Gross and Zagier, except everything is not over q. So instead of log q, we have log of uq, one of these gross Stark units, an algebraic number in the compositum of these two ring class fields. So maybe I'll leave you at that with just a couple of comments without writing anything else down. You see that already this has a couple of very nice consequences, this kind of statement, with the same kind of mechanism that Gross and Zagier used. What Gross and Zagier used is once they had this formula, well, they did many things, but this simple step that I told you about is they concluded that it was actually equal to 0. We'd love to conclude that also, Except, of course, we're landing in a space that's not necessarily 0. But for some primes, the space is trivial, namely 2, 3, 5, 7, and 13. For all those primes, the space is trivial. So you get exactly the same conclusion. You get that the norms of these invariants that we have are exactly given by essentially the combinations you get when you exponentiate this. So the UQs raise to the power the intersection numbers of geodesics on this Shimura curves. So in the situations where P is a genus 0 prime, which is really the situation that we stated most of the conjectures about in our original paper, you get exactly that conclusion back, at least for the norm to QP of these invariants. So you get, in effect, the proof of those factorization conjectures in the precise form, which I haven't given you today. But a second point is maybe even more interesting than a proof of the conjectures, because it's very suggestive. If you look at this work, there was also an interpretation of all these computations. You get contributions at various primes, various places, one contribution at infinity, being essentially the evaluation of the Green's function, and then all these contributions at the finite prime. What's the interpretation of this? We have a similar decomposition, but we have a pair of geodesics on a modular curve, so we have no idea how to attach a p-adic height to that. But it behaves formally exactly like that. So it has all these local contributions, we add them up, but the global meaning of that as a geometric object is very suggestive, certainly. So I think this proof also suggests that there is room for interpretation of these invariants in a very geometric way that is akin maybe to the way that Gross and Zagier later on continued their work and went on to the computation of the Néron heights of the Higgs, which were already defined in their case. But for us, it's a bit of a mysterious quantity that we don't really know the meaning of. Okay, so with that said, I think I'll stop there, and thanks very much for your attention.
Great talk. Does anyone have any questions or remarks? Davide?
Thanks for the great talk. So I guess I have two questions that are maybe the same one in disguise. So how much do you expect this invariant theta p cross, etc., to depend on the auxiliary prime p? So do you expect it to be completely independent of p, or?
No. It varies wildly with p. In fact, if you believe the factorization conjectures that we stated, you can actually see that if p gets really, really large with respect to the two discriminants, then automatically this is going to be trivial, maybe, or it could be. So it varies very wildly with p, and in fact, the richest behavior you seem to get the smaller prime the prime p is. So the two-adic invariants always have the richest factorizations. By the explicit form of what these intersections are exactly, which I didn't tell you about, you can see that quite clearly. So you expect the richest invariants of the two-adic case, and then three-adic case, etc. But as the prime grows, you get poorer and poorer invariants, because for a prime to divide the invariant, something has to happen. So there's essentially, well, maybe let me just tell you instead of describing it so clumsily. Any prime q arising in the factorization must be a divisor, for instance, of a number of this form, an integer number of this form that's positive. There's finitely many such numbers. And as p grows, you see you don't have a chance anymore.
And the related question, if I can ask it quickly, is that, so as you say, you have these somehow different descriptions of different factorizations that all involve intersection numbers of geodesics on different curves. So does this give you some sort of, I'll say, reciprocity law for how these numbers behave?
Yeah, absolutely. Yeah, because you see, yeah, that's very interesting that you spotted that. But these intersection numbers on XPQ, you see that essentially they don't really care about which one is P and which one is Q, because it's intersections of these geodesics associated to tau 1 and tau 2. So if you switch P and Q, you expect roughly the same thing, except the intersection numbers are also weighted in some way at Q. So there is a privileged way. I didn't tell you what the intersection number is. It's usually symmetrical, and you can see that very clearly in experiments, but especially as you're dealing with small primes, sometimes these multiplicities can grow a little bit, and the symmetry is just slightly broken, but only slightly. Yeah. It's well spotted. Yeah.
Thank you.
Other question?
So I just have a question about this formula. So the left-hand side is in QP, but these UQs are not necessarily in QP, but somehow.
Sorry, yes, sorry. There should be a norm here also. Yes.
Okay.
Yeah. Yes. Wishful thinking. I would love to not have this norm, but unfortunately it's there. Yeah.
No questions?
Yeah, we don't, I think we just compute them really by hand. We don't use any machinery to compute these intersection numbers, especially because they're not intersection numbers of algebraic cycles. Typically, anything you see in the Kudla program, you would want to evaluate something at an algebraic cycle. But for us, we're sort of in odd real dimension. We're dealing with real quadratic geodesics. And so there's no algebraic cycle in sight, really. The only invariance that we have is a geodesic associated to tau1 going from tau1 to its conjugate and quotients thereof on the corresponding Shimura. So it's true that maybe you're thinking of this Kudla-Milson theta lifts, which, yeah, indeed. So there's real analytic instructions. And in fact, so in a previous work, I didn't mention this, but just in the real quadratic case, we also have an argument just with Eisenstein series. So it's a bit more classical. With Darmon and Alice Pozzi, we have also an argument using an Eisenstein series to say something about the elliptic units in certain cases. So kind of a much weaker version of the work of Dasgupta-Kagde. And in that work, you can interpret also the series that we cook up as a Kudla-Milson theta lift. And so this was recently done by Branchereau, Romain Branchereau, a student of Bergeron. So he gave an interpretation essentially with a similar theta lifting mechanism to produce the series that we produce and to show formally the generating series of the intersection numbers that we get is the diagonal restriction of these Eisenstein series that we can see, which is one of the ingredients of the proof. So here, likewise, you can imagine proving something like that, but it'll be only about the specialization. So if I take this theta series here, I told you, and S is equal to 0, it doesn't have to vanish. And in fact, if you take the diagonal restriction, you get the generating series of the intersection numbers between the geodesic of tau1 and the Hecke translates of the geodesics of tau2. And that's something you can see through this seesaw duality. So that's where maybe the Kudla-Milson mechanism is hidden. Once you restricted the diagonal, so you lift and then you restricted the diagonal, that by seesaw duality should be the same as taking the Poincaré series here, lifting it here. This is a B star cross B star, and then pairing it with the torus, which comes out to be exactly those intersection numbers. So that would give you a kind of Branchereau style proof, but only of the diagonal restriction of the specialization. Yeah. So maybe, okay, maybe the best way to interpret this, let me write just down a small series here to clarify what I'm about to say. So if you take this theta s, and you restrict to the diagonal, and you take the first order derivative, and then you take the ordinary projection. That's the series we consider. But if you don't take just the first order derivative, but also the specialization, what you get is you get q to the n, essentially, of the intersection number of this geodesic, so the geodesic of tau1, with Tn of the geodesic of tau2. So you get a specialization that's not necessarily non-vanishing, or some quaternion algebra B, plus S times the series that I wrote down there. So you get some sort of pairing, like a fake height pairing, whatever it might mean, between this tau1 and its Hecke translates as well. So I'll put height in brackets because we don't have such an interpretation, q to the n. So that's kind of the full series. We're only looking at the first order derivative. So you might think of this height pairing as a derived version of the intersection pairing on the geodesics after you take the first order derivative. So these guys are there. There's more of a classical kind of integral quantity. These guys, the contribution at P is precisely what we constructed in the first paper with Darmon. But then we have also these contributions at Q. And we were primarily interested in cases where the height pairing was trivial, so that the analytic object we defined was actually algebraic. But maybe one could argue that in fact, it's the least interesting case, because it's the cases where the height pairing is non-vanishing, maybe, that carry more arithmetic information, but we don't really know how to interpret them. This derived pairing is a bit of a mysterious thing. It's formally defined.
So I guess no more questions. So let's think this figure again.